Good morning to everyone. Today I am discussing about quotient group or factor group. The statement of the theorem is, if H is a normal subgroup of G, then prove that G by H of all cosets of H in G with respect to coset multiplication is a group. So now first let G be a group and H be a normal subgroup of a group G, and G by H is equal to HA such that A belongs to G be the set of all cosets of H in G. Now we have to show that G by H is a group. So first we have to define a coset multiplication on G by H as HA dot HB is equal to HAB for all HA comma HB belongs to G by H and A comma B belongs to G and G is a group. So first we have to show that G by H is a group. For group we have to prove the four properties. First one, closure law, associative law and identity law and existence of inverse law. Closure law. Closure law, A comma B belongs to G implies A dot B belongs to G. So here we have to show that HA comma HB belongs to G by H and A comma B belongs to G. HA dot HB is equal to HAB. HAB belongs to G by H. Therefore, dot is closure law on G by H. And associative law. HA comma HB comma HC belongs to G by H and A comma B comma C belongs to G. HA dot HB dot HC is equal to HA into HB dot HC becomes HBC. So again we have to apply on coset multiplication. HA of BC that is equal to HAB into HC. So again we have to apply on that property HA dot HB dot HC. Therefore dot satisfies associative law on G by H. Existence of identity. Let G by H is equal to HA belongs to G by H and A belongs to G. G is a group, therefore E belongs to G. Implies HE belongs to G by H. Why? Because E is the identity. In multiplication, identity is 1. Therefore, H dot 1 is equal to H. Therefore, we have to write HE belongs to G by H. Therefore, HA dot HE is equal to HAE that is equal to HA. Therefore, HE is the identity in G by H. Existence of inverse. Let HA belongs to G by H and A belongs to G and A inverse belongs to G. So G is a group and A inverse belongs to G. Therefore HA inverse belongs to G by H. HA dot HA inverse is equal to HAA inverse that is equal to HE. HA inverse is the inverse of HA in G by H. Hence the inverse of each element exists in G by H. G by H is a group with respect to coset multiplication. Therefore, hence the proof of the quotient group or factor group of a theorem. After that, a small definition. Let G be a normal subgroup of a G, comma dot, and HA is the right coset of G and AH is the left coset of H in G. So, H is normal. HA is equal to AH. HA is equal to AH. Thus, G by H is the set of all cosets of H in G. So, define a operation coset multiplication on G by H. Coset multiplication on G by H such that HA comma HB belongs to G by H. HA dot HB is equal to HAB. So, now G by H is a group with respect to the coset multiplication. This is called quotient group or factor group of G by H. Now, a small theorem I am discussing about. If H is a normal subgroup of the finite group G, then prove that order of G by H is equal to order of G by order of H. So, let G be a finite group and H be a normal subgroup of G. Therefore, G by H is equal to HA such that A belongs to G is a quotient group. Order of G by H is equal to the number of distinct right cosets of H in G. The number of elements in G divided by the number of elements in H. Since by Lagrange's theorem, order of G divides order of H. Therefore, order of G by H is equal to order of G divided by order of H. Next theorem, prove that every quotient group of an abelian group is abelian. Let G be an abelian group and H be a subgroup of a group G. So we know that every subgroup of an abelian group is abelian. So H is a normal subgroup of G and G by H is equal to HA such that A belongs to G is a quotient group. Now we have to prove that G by H is abelian group. HA comma HB belongs to G by H. A comma B belongs to G. HA dot HB is equal to HAB, that is equal to HBA. HB dot HA. Therefore, G by HA dot HB is equal to HB dot HA. Therefore, G by H is abelian group. Therefore, every quotient group of an abelian group is abelian.